but these are actually not usually called solutions, but we will still call them classical solutions. You will see why. We will just call them special singular solutions, okay, to the Euler Lagrange equations of motion. So, again we will go back to our canonical example, that of a scalar field where the action is just given as follows. So, we will only add a quadratic piece. This I call this the mass term, because we want to preserve linearity in the Euler Lagrange equation that we will get. If you add a phi cubed or a phi fourth kind of term, the equations become non-linear. But I will also add to this an extra term, a source term. Rho of x is not supposed to be a field, it is just something external which you are putting in there, and phi is of course the field. I am here, I am not written the argument, but obviously all of them depend on x. So, that okay. So, the Euler Lagrange equation of motion for this is basically, so we have already done this once, but let me just write it out. So, we can write it in this fashion or equivalently. So, this term will give you a box phi, and now we have to take a derivative of phi with respect to this. So, you get a term which is minus m square phi of x times okay, minus rho of x. So, this term, as you can see, is giving a term which is independent of the field phi. So, I will rearrange things to get okay. So, as promised, this is linear in phi, it is a linear equation in phi, but there is a source term. So, let us just look at what this equation reduces to. So, for instance, consider a situation where phi is time independent, and then box, which basically corresponds to this following operator acting on phi. If it were phi was time independent, then you end up getting, so this equation becomes minus del square plus m square of phi of x equal to minus rho of x. Okay. Of course, to get a solution of this kind, rho better also be time independent, otherwise you cannot satisfy this equation, but that is not why. I am just trying to show you that. So, you can see that this is and let us also for a moment consider m equal to 0, then you see that just this equation becomes Poisson's equation. So, for m equal to 0, it reduces to Poisson's equation. This is an equation you would have solved in your electrodynamics course, for instance. Okay. And I guess with the m square, it is called the Helmholtz equation. I am not good with names, but I think it is called the Helmholtz equation. So, you can see that this is a natural generalization of all these things. It just takes into account invariance under special relativity. So, obviously, it tells you got to put this. Okay. By the way, I always like to write del square as minus del square. The reason is that this is the operator which is Hermitian. If you did not put the minus sign, then okay, and which is positive definite to be more important. This is the positive definite operator. This minus del square is positive as eigenvalues which are greater than or equal to 0. So, and come to think, I mean, if you think about it, even in quantum mechanics, this is exactly what happens. Okay. And I just want to again reiterate what I said last lecture. We will be always working in what are called natural units. Not just CFT in quantum field theory. So, the first one is to work in units where C is equal to 1. Okay. Then time, and in such units time and space are measured in the same this thing. And in this course we will not use quite a bit of this, but you can also set h bar equal to 1. So, this is an extra this thing. Okay. So, so for instance, in such situations you can see that energy. So, let us look at this first. If you look at a relation like energy and mass, you get E equal to mc square just for dimensional grounds. So, C is equal to 1. So, E and m are measured in the same units. Okay. So, you can say mass in GeV, or you could say energy in kilograms. Okay. But it is more common to work with mass etc. in this thing. So, you can also see that E dimensionally is the same as P times C. Again, momentum is also measured in terms of mass units or energy units. So, this is these are nice things which happen. Similarly, if you put h bar equal to 1, so let us look at a few more things, something like h e equal to h nu or h cross h bar omega. So, you can see that energy is the same as 1 by time. Okay. But from since we are putting C equal to 1, it is like 1 by length. Okay. So, because of these things, what we will call the physical dimensions usually were mass and L, but in these sort of things they have an inverse relationship. So, okay. And intuitively this is very nice. This tells you that if you have high energy or high mass, that is like lower length scale. Okay. So, that is what they say, that when you are probing the quantum nature of matter, you are probing at lower length scales or higher energies. Okay. So, intuitively this is what. So, this is the units which are natural in quantum field theory, but these are not the natural units in the general theory of relativity, because h bar, it is a classical theory, h bar is a constant that does not come in that theory. So, what is natural to general relativity would be fine to set C equal to 1, because SR sits inside that, but there is the Newton's constant. So, you go ahead and set G Newton equal to 1. So, you measure everything in terms and then there you get something very counterintuitive to this, that M and L are actually the same. Okay. So, but in this course we will be always setting these two constants equal to 1, and that is what is natural to this course. Okay. Yeah. So, so for the rest of this course I will never, I mean unless necessary I will not put these factors back, and but it is not very hard to put them back either. Okay. And h bar will not come except in isolated instances when I want to make remarks. Okay. But otherwise C will be equal to 1. Okay. So, we need to solve this equation, and so this equation is a inhomogeneous Klein-Gordon equation. The homogeneous equation is when the source term is 0. Okay. So, if you have done a course in differential equations, you will know that there is something called a general solution and a particular solution. Okay. And so, even out here let us sort of denote, let phi h denote a solution to the homogeneous or Klein-Gordon equation. In other words, it satisfies this equation with no sources, and phi p denote the particular solution to the inhomogeneous equation to okay. But because of the linearity of this equation, any arbitrary solution and so let us call this equation star will be of the form phi arbitrary solution will be some linear combination of a given particular solution and the homogeneous solution. So, if you give me two different solutions, another way of saying it is if I take two different solutions to this equation, you take their difference, it is easy to show that it satisfies the other equation, that is the homogeneous Klein-Gordon equation. Okay. So, what we will do is to try to solve for this equation, but we will solve it through a method of called the green function. So, we will use the method of green functions. Okay, this generalizes so coming back to Poisson's equation, what we would do in electrostatics is to solve, if you know the answer for a point charge, okay, we can write out the answer for an arbitrary charge distribution. Okay. What is a point charge? It is a delta function source. So, we will do the same thing out here, we will choose a delta function source and try to solve not that equation, but this equation, okay, and we will call that the green function. Books call it the Green's function, but I mean I think it should be called the green function, like the color green. So, wherever I saw this rho of x, I just go ahead and solve for a okay. So, this is a d plus 1 dimensional Dirac delta function. So, in other words, you have a source at some point in space and time, not just space like you would in these sort of equations, but in this equation. Okay. So, suppose, and so you can see that this object here g of x prime has two arguments, that is in part because this location is an independent quantity. Okay. So, this is the equation we would like to solve, and it is very easy to see. Suppose you give me such a g, then I can give you a solution to this equation. Okay. So, given we can, I will put solve in quotes because it is really not, I would not call it a solution yet, solve equation star as follows. So, you just write, consider the following thing, phi of x equal to integral over all Okay, so let me just do one thing. Let me put a minus sign out here. Okay, so I saw the reason is I just want to put rho as some delta function. So that would, I just want to keep the minus sign elsewhere. So it's not hard to see that this satisfies the equation star. Yes, the integral is over x prime. Okay, but the key point is that one more reason to say that put quotes under solve is because I mean a differential equation is not I mean it is not well posed until you put boundary conditions, etc. Okay, so you need to put the boundary conditions, and that comes back to this splitting. So this, it looks like that you have an infinite set of solutions, but in fact that is not true. Once you give a proper set of boundary conditions, it will uniquely fix if, what phi h should be. You do not have any freedom. Okay, all the ambiguity that is there is gone. Okay. So coming back to this problem, we would like to ask what are the good boundary conditions, etc. We have discussed a little bit when we were getting the equations of motion, the surface terms had to vanish. That usually is a good set of boundary conditions, and it is a very nice way of actually deriving things, the what are the good boundary conditions. So the first step is to actually go ahead and work out what g of x prime is. Okay. But before that, let us try to understand some properties of this. So let us see what are the properties of the green function. Okay, so the first thing is since it is a green function, for the scalar field we take it to be a Lorentz scalar. Okay, if you change coordinates, if you go from coordinates x to some x tilde and similarly x prime to x tilde prime, then g should change as follows. Okay. Second bit is you have translation invariance. You can see out here, if you shift both x and x prime simultaneously by a constant, the source is I mean it depends only on the difference. So similarly, translation invariance implies that g should be only a function of the differences. Okay. So you may wonder where I am going to use this. We will see a little later that we can use all these symmetries, and it is enough to check for instance, if we want some properties of g, suppose we say that g should vanish in some region, okay, then you might be able to check, it might be easy to check for some parts of the region, and by the rest we will just say that because it is Lorentz scalar it follows. But you can go back, and if you do not believe that, you can actually do it the hard way and prove that it vanishes in other regions. Okay. So let us see where it should vanish. So let us look at this. So as it stands, this is kind of non-local. Look here, x and x prime are two different space time points, they need not even be causally connected. Okay. So what you are saying is that if so, this is one way of understanding this is if you create some perturbation or something at x prime, it is affecting something at some other space time point. Now what would causality tell you? That x should be in the past, in the future of x prime, otherwise if such things did not influence things, then this we would get causality violation. Suppose x prime was in the future, that means this field already knows about something in the future. Okay, so for instance, so let's see what causality tells you. So that is the third thing. So I will write something outside the light cone first. So let me remind you what the light cone is. So I will draw it for one space and one time, but you can extend it to arbitrary space dimensions. Okay. So this so since we are working in units where c is equal to 1, a ray of light can move at will move at the trajectory of a ray of light would be, suppose you emitted a photon here, it will move along this line, this is at 45 degrees with slope 1 or minus 1, depends on which direction it is moving, minus x or this. Okay. So dx by dt is 1. Okay. So this, okay. So the point is, so the thing is, all events which can be influenced in the future by points here have to lie inside the light cone, because nothing can go faster than the speed of light. Okay. So these regions cannot be affected by points here. I mean, a dramatic case is someone is sitting here and someone is sitting in the nearest in Alpha Centauri or something like that at the same time. There is no way this person could influence this. Okay. You have to wait, at least if you send a light ray, you have to extend this. So let us put it here. It will take some time to come, even a light ray would come much later in the future, but we are talking about this space time point. So this space time point is causally disconnected to this thing. Okay. So what we say is the points which can be affected, so this is called the future light cone. The reason it is called a cone is, suppose you have a y direction, let me add that, coming out of the board, then you can spin this thing and you get a object which looks like a cone. In higher dimensions you call it some hypercone or something, nobody calls it hyper something, you just call it a cone. It is just to remind you of what it is. Here in this picture it is only like a sort of a wedge. Okay. The wedge becomes a cone. So points which lie in the future of this point are called the future light cone, and points which lie in the past of it would be called the past light cone. Okay. Causality, I mean, first thing is anything outside the light cone. Okay. So here let us actually plot x minus x prime, because it is a difference of things. So when x equal to x prime, that would be the origin out here. So we are asking what are all the points x prime can affect. It can affect only things in the future light cone, and it cannot affect things in the past light cone. Okay. So this tells you that g here should vanish outside the light cone, number 1. It should also vanish in the past light cone. So by that I mean g of x minus x prime equal to 0 when t minus t prime is less than 0. Okay. So it should only vanish in one of these things, and we will just call such a object, we will say that we will call it the retarded RET for retarded Green function. Okay. It takes the retardation effects into account. Okay. But sometimes you are solving an inverse problem, you are solving something where you know the answer now, but you want to know what was the object in the previous what was the thing which created this today, then you would look at something which does the opposite. Okay, that is called the advanced thing that will not vanish, that will vanish when t prime minus t is less than 0, the other combination. So, the question is how do we go about solving for this, but already we have when you are solving Laplace's equation or Poisson's equation, the natural thing is to take the Fourier transform. So, here we will do exactly that, we will take the d plus 1 dimensional Fourier transform. Okay. What it does for you is to convert all differential equations into algebraic equations. Okay. So, let us do that, let us define okay. So, k here is a 4 vector which I will write as omega and some spatial vector k. Okay. So, k mu x mu this would be omega t where again the usual thing, the x0 coordinate is called t and the spatial is some vector. So, this vector will be as many dimensions, spatial dimensions as you have, okay. And this minus sign is a signature which we will follow. We are going dd plus 1 of k, thank you. Okay. So, now we have to plug this into the equation. So, we will plug it into equation star, which I have erased, but hopefully you have it in your books, and the formula are very easy in the following sense that dt square. So, we just have to use dt acting on this will pull down, should be replaced by what minus I omega, and d and the del operator, the nabla, should get replaced by plus okay. Remember it was acting on the first guy x prime is was just there for the right. So, we can see that the box operator which was dt square minus del square just becomes minus omega square and okay. So, this is not bad. Oh, but we do not want to plug it into star, actually we want to plug it into this equation, right. So, it is not star, but into this particular equation, into this equation. So, luckily I have it on the board. So, now we can see that we can just go ahead and let me define this particular combination will keep coming again and again, and we let us define this to be minus omega k square. So, in other words omega k square is defined to be we also need to use one more thing, we need a representation of the delta function, but that is not so hard, it is just it's the transform of 1, okay, and that is a 2 pi power d plus 1. So, delta function in case you have forgotten, there it has a 2 pi times e power I minus I k dot x minus x prime. Okay. So now we have written everything in terms of these guys. So what this tells you is that this side will just be minus 1 in the algebraic equation, while this will be these particular various operators. So let me just put that in. So what we will get is an integral so let us just stick to this. So that comes from this plus m square into g tilde of k into e power so that is the left hand side of this equation, and the right hand side is just this. So I will just what I will do now is to erase this because I am running out of space, and say that minus of this is equal to this. Okay. So this equation, all I have done is put g of x, I have substituted this in here, and then I have written out what the operator gives. So now the key point here is that this holds for every k. So you get an algebraic equation which is just the coefficient of e power minus I k dot x into x prime. So you get an algebraic equation for g tilde of k, which I will write out here. I want this combination to be a m square omega k square. So I will just do this first. So all we have done really is by going to the Fourier transform, we have transformed this equation, which is a differential equation, to this equation which is an algebraic equation in k for g tilde of k. And if you are able to solve for g tilde of k, then we can do the inverse Fourier transform and get back g of x prime. Okay. So this will just tell you that g tilde of k is 1 by this is what I wanted to define as omega k square. Sometimes one is just jumping steps in one's mind. So, okay, so this is what you get. So you get something very, very simple. Okay, is this clear? So just remember that omega k is only a function of the 3 vectors, and this m is a constant. Okay. So we are almost done, but we need to be. So if you are done, so since we have already solved now for g tilde of k, remember every solved I am saying has a quote in it because we have really not put in any boundary conditions, etc., and we will see how to do it. So now that we have got this guy, we can plug things back into the other equation, and so now we have our what I call a formal solution. There is some powers of 2 pi, right? Yeah, so let me do this. Let me put the 2 pi power d plus 1 here also, so that I don't they get cancelled away. Otherwise, we have to keep carrying these annoying powers of 2 pi. Okay, just my definition of g tilde. Okay, so then this has a simple form. Okay. So now we need to go ahead and do this integration, but what we will do here is not do the complete integration, at least I will not do it. but I may give it as an exercise for you. And so, I will do the omega integration, and we will see that I can incorporate for instance issues like causality right away. Okay. So, the first thing to do is so the plan is just carry out the omega integration and I will use the method use complex method. So, using contour integrals. Okay. For this I just need only one formula which says that if you have a so let us just write the omega some f of some omega naught, and let us say we have some closed contour. So, omega, think of omega as some complex number. So, I have this is omega is the complex plane. Here of course, omega is real, but what we will do is we will think of omega as a complex number, and that helps you. And suppose omega naught is something out here. Okay. So, the point is that, and we will pick some contours. So, there could be a contour like this, and choose the orientation to be counterclockwise. If you change orientation, the answer is minus of that thing. So, let us say gamma like this, let us call it gamma 1. Let us say we have another contour which does not enclose this. Okay. So, there were two possibilities. So, let us look at gamma 1 and gamma 2. Standard results from complex analysis tell you that if the contour encloses the pole, this pole, then the answer is 2 pi I, and otherwise it is 0. For gamma 1 and 0 for gamma 2. Okay. So, there is a 2 pi I, which I forget something 2 pi I times f of omega naught, called the residue of the pole. Okay. And if you have gamma the same contour going the other way, you would write, you could think of it as minus gamma 1, and then the answer will be minus of it. You could have contours which wind n times with positive this thing, then you will get n times that answer, but it all follows from basic property of integrals that if you you can always break up an integral into separate sums. So, if you have something which winds around this n times, that is equal to n times 1 going around once. Okay. And n equal to minus 1 is a special case. Okay. So, we want to do that. So, we will just carry out the integration, but we have several issues. First thing is that so the omega integration runs from minus infinity to plus infinity on the real omega axis. Okay. And this has two poles, one at omega equal to plus omega k and minus omega k, and so we can use the method of partial fractions to split this. So, this is just the fancy term for this, the simple elementary formula which says that okay. So, now you can see that if I focus on the omega integration, of 2 pi I into, of course, okay. So, now you can see that and omega integration goes from minus infinity to plus infinity. So, now you can see that at least I have brought it into some form like this f of omega, where f of omega is just this e power I the omega into t minus t prime, that is what is the only omega dependent part, or you call this f of omega and you get it as a sum of two terms. So, we have to do two separate contour integrals, but we do not have a contour. What we have is a integration which is a line, a contour should have a closure. Okay. So, what we will do is to look at the structure we have out here, and there is a minus here. Okay. Even in the partial fraction there is a minus sign. Yes, this minus sign you mean. Okay, thank you. Yeah, all these signs are very important, and I keep dropping signs obviously. Okay, so, now we need to just do this, and the trick is very nice. It is more than a trick, it is an important method of solving this, of doing this integral. So, since it is important, I will plot this thing. So, what we have is, let me use a different color here. So, we have a contour which runs like this. This is minus infinity and plus infinity. This is omega real and omega imaginary. Okay. But first thing is we already have a problem. We have a problem that our contour runs through these poles. So, there is this is at omega equal to plus omega k, and it has two poles, another at minus omega k. But let us do things one at a time. Let us first convert it to a closed contour. So, let us look at the omega dependent part of this. So, it is e power minus omega into I omega into t minus t prime. Okay, and we have taken omega to be complex. So, what we will do here is try to add to it a semicircle. By a semicircle I mean, first think of this as a contour which has some finite radius, and then take r to infinity. So, I think of a infinite radius semicircle which closes either up or below. But one nice thing you can observe out here is that so if you write this out in terms of real and imaginary, you will see that this is minus I omega real into t minus t prime times e power. So, the imaginary part will give you omega into t minus t prime, omega imaginary. So, if you look out here in the upper half plane, omega imaginary is positive, okay, while in the lower half plane it is negative. So, now you can see that it if t minus t prime, if t minus t prime were negative, then this is an exponentially suppressed term in the upper half plane, while. So, let us write this out. If t minus t prime is less than 0, this exponential, so the exponential part is suppressed in the upper half plane, which I will write as UH. Okay, and the second bit is if t minus t prime is greater than 0, there is exponential suppression in a lower half plane. Okay. And now you can see that on this contour, and as the radius is becoming larger and larger, these terms do not contribute, they get suppressed, they actually go to 0. So, now you know the rule. It says that if t minus t prime is less than 0, you close the contour in the upper half plane, you are adding 0 if you wish, and if t minus t prime is greater than 0, you close the loop in the lower half plane. Okay. So, now we have solved the first problem, which is to convert our open contour into a closed contour. Okay. So, let me draw this and explain it through pictures. I will draw it as a finite thing, but you have to think of this as an infinite dimensional radius. Okay. So, this goes like this. This we can do only when okay. And again orientation, remember this is counterclockwise, so this is positive orientation, but otherwise we close it downstairs. This we can do when t minus t prime is greater than 0, okay. So now we have closed contours, but if you close in the lower half plane, the orientation is opposite, okay, it is clockwise. This is a clockwise contour. So if you have any pole out here, okay, so the question is how do we go about doing the integration, because we still have to handle one more issue, which is the fact that there are two poles on the contour, okay. So the trick here is to sort of jiggle these things up or down, okay. So I could do this, I could work, I could take this guy and move this contour. So let me use a completely different chart. I have 4 possibilities in this thing. I could move this contour slightly up, I could move it slightly down, I could do the same thing out here. There are 4 possibilities, but the question is which one of these 4 is relevant to us, because now you can see something nice. So if you look here, it is t minus t prime less than 0, that means t is less than t prime. So if you want the retardation effect to happen, what is it we would have liked? We would have liked t minus t prime to be greater than 0, okay. So for the g to not vanish, so now you can see that you can determine when these things will have to contribute. So what you have to do is to decide whether these poles contribute or not. You go back and look at your physical input, which tells you that your g advanced has to vanish somewhere, or in some other case it has to be non vanishing. So that will determine how you move these, okay. So what we will find is either moving both of them up or both of them down simultaneously will give you either the advanced or the retarded guys, but it leaves you 2 other things, and you may say that look, I am not interested in that kind of stuff, but life is not so simple. It turns out that in quantum field theory one of the other choices comes, you know, where one goes up and the other goes down, okay, and you get, I mean you might think, oh, I have got something acausal etc., but it is very interesting to see how that works. So we will discuss that also, even though there is a course in classical field theory like I mentioned, but there will be certain issues which we can discuss, okay. So what you will find is what is called the Feynman propagator corresponds to choosing the other this thing, okay. So even that does show up. So in some sense these you may think, what is all this ambiguity out here, I am able to move it at will and get different answers, but that is not the point. The point is that this corresponds to choosing your boundary conditions. If you remember in the beginning of this lecture I told you that you get a particular and a homogeneous things, the same thing holds out here. What you are doing is these you can prove if you wish, it is not so hard. If you give 2 different, you take for instance the advanced and the retarded guys, and you take their difference, that will satisfy the homogeneous equation, okay. So they all differ in the choice of the homogeneous equations, and that is determined by whatever boundary conditions that you are putting in, okay. So we still have to complete this problem, we will do it next lecture, we will carry out these integrations, we will see certain properties, okay. And now the thing is, you may say that, you know, it might be true in one frame I have done this, in some other frame this may not hold, okay. And this is where I will appeal to the first point I made, is that the green function is Lorentz invariant. So if it vanishes outside the light cone at one point, you can actually play around with it and you can show that it vanishes everywhere. So basically what we will show is that if it vanishes on one curve, one line in the outside the light cone, it has to vanish. That curve can be made into any other point in the light cone by changing things, okay. So in some sense it is enough for us to do this. I will discuss this in a little bit more detail next lecture. So next lecture we will complete this story, we will also see what this Feynman propagator is, and we will so then we can go about carrying out these integrals, but we still will have to do the spatial integrals, and some of it can be done, some of it cannot be done. Well, cannot is wrong, because you could write things in terms of Bessel functions and things like that, but it is a little bit involved, but you can carry out, in principle you could carry out the integrations, okay. I am done.